Hi, my name is Sydney Kerckhove. I'm working at FP Complete right now, and I have the good fortune of writing a lot of tests as part of my day job. I write a lot of property tests, and I've noticed a big difference between the reality of property testing and what you see in papers. So that's what I'm going to be talking about today. Now, Michael is in the panel as well, and he will be able to relay questions to me via the Q&A part of Zoom. I think we're ready to get started. All right. So I have the good fortune of writing a lot of property tests, but it turns out that there is a big difference between what you see in the property testing papers or what you see in the tutorials and how things actually work in reality. And I'd like to to talk about the difference and how it actually works in reality and why it's actually pretty cool and what you can do that you don't see in the tutorials that can make your life easier while working with property tests. First, I'm going to explain what property tests are and why we use them. I'm going to just skim over this because I'm assuming that everyone has done a little bit of property testing. I want to dig into how you use them and what the pitfalls are when using them. So I'm going to have to dive into the internal workings of property testing to make sure that we're on the same page of how these things work. And then I'm going to go into the first aspect of property testing that we don't usually see in papers or in tutorials, which is a way to reuse property testing such that you only have to write very little testing code in order to use the same kind of test in a lot of your project. And then at the end, I'm going to talk about how you use property testing in the case of a web service that uses a database. So a real-world example of how you would actually use property testing for a commercial product. And then I'm going to link to a few relevant projects at the end that you may want to look at afterwards. So let's have a look at the difference between unit testing and property testing. In a unit test, you just write a piece of code, and if the piece of code does not crash, then it passes the test. If it does crash, then it doesn't pass the test. And then here is an example of a unit test. Here we say that if you reverse the list 173 twice, you should get that list again. This should be a function test that those two are equal, and it's just an easy way to make that piece of code crash. The only difference with a property test is that instead of just giving one example, now your piece of code has an argument, and the test should pass for whatever argument is passed into that property. The property you see here, it says that if you reverse a list twice, any list, then it should be the original list that you get back. Now, why would you use such a thing? When you generate examples to test, you get a lot of examples in a lot more cheaper of a way than to think of all of them yourself. And the random generator will actually come up with a lot of examples that you would never have thought of. It will also come up with edge cases, depending on how the generator is set up. But if you use the default generators, then for any list that you use, it will also test what happens if you use the empty list, for example. So you can make sure that you don't have to be smart enough to come up with all the ways that your code can fail. You can sometimes use the randomness generator and find new bugs that you haven't even thought of, which is different from in unit tests. Now, why wouldn't you use this? You have to come up with the general properties now. You don't just come up with examples of input and output. You have to come up with an abstract mathematical generalized property of your code, which can be a bit more tricky in the beginning. And now you have to think of generators and shrinking. And it turns out there are some pitfalls there. I'm just looking on my other screen in the meantime to make sure that there aren't any questions being relayed from Michael here. All right, so let's have a look at an example of a property test. Here is an example of how you could run a property test with QuickCheck. This piece of code just uses QuickCheck to test that the property we just saw, that if you reverse a list twice, it gives you the original list, to check that this holds. QuickCheck will automatically generate 100 different inputs and then check if the property holds for those inputs. And we can see that this property indeed seems to hold. QuickCheck uses two things, a generator and a shrinking strategy. I will get into the shrinking later. Let's first have a look at how these generators work on the inside. A generator of A's will generate A's. but it uses two pieces of input. First, it uses a seed to make sure that the generation is deterministic so that you can reproduce generating certain values with if you have the original seed. And it also uses what we call a size. The size is used to guide the generation of the values in the case that there are an infinite number of values that could be generated that differ based on their size. For example, if you want to generate any list uniformly from the set of lists, you'll get in trouble because lists can be arbitrarily long. But if you have a size parameter that you can use to dictate how long the list should be, then you can generate an arbitrary list. So that's why what the size is for. But the size thing can actually get you into trouble, and we'll get to that in a moment. But let's go on to the shrinking strategy. So what happens if a property test fails? Here's an example of a nice property that will fail. This property says that if you uppercase all characters in a string, then all the elements of that string will become uppercased. And QuickCheck can test this and says, no, that's not true. And here's a counterexample of a string that doesn't satisfy this property. If you only see the string as the counterexample to your property, you may be confused. It will be very hard to figure out what went wrong just from the string. So what QuickCheck does when it finds a counterexample is it tries to shrink this value by generating the list of all, producing the list of all the elements that are in some sense smaller than the original counterexample. We'll get back to what smaller really means, but if QuickCheck finds a counterexample, it will try to shrink this counterexample to a smaller counterexample that still fails the test, but is now more manageable to look at to see what the actual problem is. So if you turn shrinking back on, then this is what you'll see as output. After 3 tests, QuickCheck will find a string that is problematic, and then it will try to shrink it. And in this case, it has shrunk the counterexample to the string of the character that only contains a 1. Now, if you have a look at it, if you uppercase a 1, it just stays a 1. If you then check if it's uppercase, GHC will tell you that the character 1 is not in fact uppercase. Fun fact, it's also not lowercase, so you could get into trouble if you expect stuff like this. Now, QuickCheck allocates a number of tries that it can do to try and shrink the given counterexample. It will produce this list of smaller values, and it will go through them from front to back. And if for any value that still fails, it will choose that as a new counterexample. So it will generate this list, go over them one by one, look if they still fail, and the first value that still fails the test, it will use as a new counterexample. If there are still tries left for the shrinking, then it will go on and try to shrink recursively until the tries are over. Now, this was the explanation of how property testing can be run with QuickCheck if you only use the default generators, if you don't want to worry about that, and if you only use the default shrinking. But you can also use your own custom generators, and you would use this when a certain property only holds for a specific kind of values. Let's see how we can make our own custom generators. There are 3 building blocks that I want to talk about here. First, there is the arbitrary generator, which for any type that QuickCheck knows about how to generate one of them is a generator of arbitrary values of that type. Then there is the such_that function that takes a generator and a predicate and filters the values that are being generated through that predicate. And that happens as follows. You generate a single value, you see if the value satisfies the predicate. If it does satisfy the predicate, then you can return the value, otherwise you have to try again. And then there is the elements function, which takes a list of elements and randomly picks one with equal probability for all the elements. So here's an example of how you can use these generators, these functions to make your own generators. Here are 2 generators to generate the suit of a card and to generate the value of a card. These are playing cards, and they use the elements function. Now, generators are also applicative, so they compose nicely. So you can generate an entire card, which would just be a tuple of characters that represent the suit and the value. And you can also use these generators monadically. For example, if you want to generate a length of a list first, and then use that length of a list to generate a bunch of cards in a list. Now, I've talked about the size parameter. Suppose you would want to use those sizes for your custom generators. Then there are two building blocks you need to worry about. First, there is the sized function, which allows you to use the size parameter of the generator. To be clear, the size is not generated. It is a parameter, so QuickCheck passes it in. And this sized function allows you to use the generator by supplying a function that uses, the sized function allows you to use the size by supplying a function that uses a size and makes a generator. And the resize function allows you to pass in a new size parameter to a generator and build a generator from that ignores the original parameter that was passed in by QuickCheck. Here's a nice example. A generated list of 15 ints. You can just say replicate M15 arbitrary, but I want to show off these functions. So with sized, you have to submit a function. This function gets the size, which we will call n, and you can replicate n of these, and you can actually make the size be 15 with the resize function. I'm getting no questions, so I'm assuming everything is clear. Now, suppose we have written our own custom generators. Then here is an example of how you would use that. The forAll function can make a generator, a new property, given that you give it a generator and a property that uses a value that you get from this property. So here's an example. For all of my custom generator, test this property of the value that you get out of the property out of the generator. Suppose you also use a custom shrinking strategy, then you use forAll shrink, which is where you can also supply your own shrinking strategy. Now you may ask, why would I make my own shrinking strategy? Because that seems like a lot of work, and I don't really care if my values are smaller. Even if you don't care that the values that you look at as a counterexample are smaller, you need to care about shrinking if you write your custom generators. And here's the reason. Suppose I have the belief that every number larger than 5 is both larger than 5 and even. And I want to test whether this is true. Then I can write a property test like the one I've made here, where I say that for all arbitrary integers that are larger than 5, so that's the custom generator. And suppose that I use a custom shrinking strategy, but as the custom shrinking strategy, I will use the default shrinking strategy instead of none of them, no shrinking strategy. Then here's what will happen. QuickCheck will say, I've run this property and it doesn't hold. Here is a counterexample. The counterexample is 0. And you may look at this and think, hold on, I was thinking about only values that are larger than 5. Why is it giving me 0? Well, if it had generated a value larger than 5, say 6, 6 is indeed even, so it's a bad example. Let's say 7 is generated. 7 is indeed larger than 5, and it's not even, so QuickCheck will use this as a counterexample. Now, because it's found a counterexample and it has a shrinking strategy, it will try to shrink 7 to something smaller. For example, 7 can be shrunk to 0. It will then test the property again for 0. 0 is not larger than 5, so it's another counterexample, but 0 is the smallest integer that we shrink to, so it doesn't try to shrink any further. And then it reports, oh, here's a counterexample, 0 is a counterexample. But this is a problem when you try to debug this, because 0 fails the property for a different reason than 7 does. So it's important that when you write a custom generator, that you use a shrinking function that maintains the invariance of the generator. So when you would write a custom shrinking function here, when you would use a custom shrinking function, you have to make sure that the values that are shrunk to are also still larger than 5. And you can do that by filtering through the result of the shrinking function with the predicate greater than 5 that you want to have hold for all of the values that you shrink to. Let's have a look at the dangers of writing your own generators. Suppose you use such that, then here are two different ways to write a generator that will only ever create values that are exactly 0 and are integers. The first generator will do no computation and just return 100. The second generator will generate a random integer, check if it's 100, and if it is 100, then return it. Otherwise, try again. So the second generator can take a very long time to generate 100, but it will still only generate 100. Now, in my experience, if the property test suite is slow, it's because you've used slow generators. And usually when you have slow generators, it's because you use such that with either, with an expensive predicate or a predicate that is rarely satisfied. Here we had an example of a predicate that is rarely satisfied. An example of an expensive predicate could be something like check if an integer is prime, or even more unreasonable, check if an integer is a busy beaver number. I don't know. There are some more dangers with property testing. This one is more general. This property says every list is smaller than 100 elements. And QuickCheck can test this, and it says, all right, this passed 100 tests. But we know that there are lists that are longer than 100 elements. So why would QuickCheck say this is fine? Well, the way you read this is not the property holds, but for all of the input cases that we tested, the property holds. And the reason is that QuickCheck uses rather small sizes. It uses sizes up to about 30, if I can remember correctly. And indeed, if you resize the generator to use something larger than what QuickCheck supplies, for example, 200, then it will say, oh, this property doesn't hold. So you have to really watch out for properties that depend on the size of the input. If your property does depend on the size of the input, you better make sure that you generate values that are large enough to make sure that this dependence does not show up as false positives. There are some more dangers with the size parameter. Let's have a look at this data type. A tree can either be a leaf or a branch with more subtrees. Let's say we look at this tree data type without any values within the tree. And suppose you would want to write your generator and you make an instance of arbitrary, but this really works for any generator. This generator says, choose one of these two generators. Either you generate a leaf and do no computation, or you generate a branch and then recursively generate the subtrees of that branch. If we now make the function size for trees that just computes the total number of leaves and branches in the tree, and we try to generate a tree of size 1 with this generator, then QuickCheck can generate very, very large trees. For example, on the second try, I got a tree that is 83,000 nodes in size. You have to watch out for any generator that uses the size non-linearly in the size of the thing that you'll actually be generating. And the way you actually do that is by using the size function that we saw before. So to write this generator, I'm going to say, I'm going to need to look at the size. If the size is smaller than or equal to 1, then generate a leaf. Otherwise, you'll have to generate a branch. And the way we do that is by first splitting the size into two numbers that are both random, but they sum to the size. And then resize the left half of the tree that to be generated to be the first number, and the right half of the tree to be generated to be the second number. And then you can create the tree as follows. You could actually make this gen split n-1, but it doesn't really matter. The point is that now this generator is linear. The size of the outputs of this generator will be linear in the size that is the parameter of the generator. That's important. All right, this is a good place to pause before I go on to property combinators and test suite combinators. If there are any questions, feel free to ask them now about this part of the talk.
I'm not seeing any questions coming in yet.
All right, no questions, then I'll just go on to property combinators. Let's say you write a custom ORD instance for your data type. Let's say your data type is called foobar, and you want to make sure that your custom ORD instance makes sense. You may write a test suite like this, where you say that larger than or equal to and smaller than or equal to are both reflexive relations. You can see that there is probably some duplication to get rid of here. And indeed, you could write a separate function that we call a property combinator, which just takes an arbitrary binary relation and checks the property that this binary relation is reflexive for any random input. And then you can rewrite this test suite like so, such that you only have to say this relation is reflexive and explain that that is what you're testing. Here are some more examples of property combinators. The first one checks that a binary operation is commutative. The second one checks that a binary relation is symmetric. So these two are the typical mathematical things you may want to check. Then there is also the property that tests if two functions are equal for all of the generated inputs. And the last example here tests that two functions are inverses for all of the generated inputs. Let's say you have more than one custom ORD instance in your library. You wouldn't want to write this entire test suite all over again every time. So there is actually a way we can reuse a test suite as well, and it's with a few tricks. Here is what I call a test suite combinator, which allows you to check whether the eq instance of a given type makes sense. Now, the implementation is rather long, so I will show you what the output is instead of the implementation in a moment, but let's have a look at the type here. The type of this test suite is for all A, where A is generatable. This is a test suite. And you can see that the A is never used in the type of expec, but it is part of the type in the constraints. This is allowed because we use scope type variables and ambiguous types. And to use this kind of test suite combinator, we have to use type applications in order to supply the type as an argument. And then you can say my test suite means that you have to run expec at the integer type. And then the output can look something like this. For all integers, equality is reflexive, symmetric, transitive, exactly what you would expect, and equality is equivalent to not equality. So you can actually reuse an entire test suite based on just the type. You can also, for example, reuse an entire test suite based on just the function and the name. We've written these for example, also for ASIN instances to make sure that if you serialize something to JSON and back, it's the same thing. Or maybe if you serialize something, you won't run into errors. These things can all be abstracted over and reused in these test suite combinators. And we use them a lot. All right, this is another nice stopping point before I go into the web service example. If there are any questions, go ahead.
Yeah, we got a question from Nick asking, why do we need this for all A part in EQ spec? I think that's one slide, yeah.
Aha, here. So you say for all A spec. If you play the role of the compiler in your head, and this would just be EQ spec is of type spec, then that would mean for all usages of EQ spec, it's a test suite, but there is no mention of the type of the thing that you're testing. So there must be a way to pass in the type of the thing that you want to test. And by using scope type variables, the implementation of expec can actually use the A that we use in for all A here to see what it is that we'll be testing. And I actually shortened the type constraint here a bit, because in reality this also says show an eq and typeable, so that you can show the name, so that you can say eq for ints automatically instead of just eq. And then these ints here are also based on the type A and the typeable instance of it. Does that make sense?
We have a follow-on question from Gabriel Garcia asking if a proxy A could have done the trick in this case.
Absolutely. Yes, it could have.
Okay, no new questions coming in right now.
All right, let's go on to the practical example of a web service. Suppose you write your web service and it uses a database and you want to test your web service. Then this is what the diagram would look like. You have it, you want to write your tests, your property tests that talk to the web service that talks to the database. So you would want the web service to be set up once, then called a bunch of times, and then torn down. And if that would make it faster, you would also be okay with the state in the database being reused across the property tests. And this is actually not a big deal if your web service depends on or has user accounts, because then you can just use a separate account every time. Now, the plan to do this is as follows. You set everything up once before the tests start running. For each of the property tests you want to run, you want to hook into this web service that you used for your tests. You can share the state across the property test, and then at the end of the test suite, you want to tear everything down. That's the plan. Now, HSpec allows you to do that, but you need a few bit of plumbing. Here's the first bit you need. We're going to set up the web service and the database and connect to it, and then expose it as a Y application in this function. We're also going to make an HTTP manager for our tests to connect to the test web service. Then suppose you have one of these tuples of an HTTP manager and a Y application. Then we need to explain to the test framework how you can run a single test, and Warp actually has a nice function for that. It's called test with application that deals with exceptions and everything for you. And the way we're going to expose the test web service to the test is by giving it this client environment that just explains how to connect to the test web service. This is also how it works in Servant, by the way, but you can do that for any others as well. So this client environment just contains the HTTP manager and the URL where to connect to the test web service. And then you run the test called func, which uses this client environment. Now, to put all these things together, we're going to make a combinator that will allow you to annotate a test suite with the idea that you may want to use the client environment to connect to a test web service. And the way you do that is you use these three functions called before all, around with, and after all. Before all just says, before starting to run any of this test suite, you first have to run this function called setupMyApp. Around every test, including every single instance of a property test, you will have to use the withMyApp function to turn the tuple that you made with the setupMyApp function into the client environment such that it can be used for the test. And at the end, you will want to clean up everything. And now let's have a look at what it looks like if you use one of these. This is the test that you would want to write, but this is a lot on the at the same time. So let's look at what you would want to write. Here is what you want to write. Let's say you have your API, and you have a single API endpoint, and you want to make sure that if you call it twice with the same argument, that you get the same result twice. So this callMyAPI function runs in a client monad that uses the client environment. Oops. So what we do is we run the client monad with the client environment. We get the two results with callMyAPI with the same argument twice, and then we check that you get the same result for every time you call the API. Now, the reason that I have to do this shuffling with returning the tuple and then unpacking the tuple again is because you cannot use should be in the client monad. Well, technically you could use lift.io, but there are reasons not to, so I've not done it here. Now, where do you get these arguments from? Well, this property should hold for any argument, so let's make a property test out of it. Here we say that for all arbitrary argument, this property should hold. Now, we still haven't gotten this client environment. Now, because we've written this combinator, we can actually assume that we can get the client environment out of the test framework. And when you write the test that says describe calling the API, it yada, 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 you can assume that it can give you this client environment out of the test framework. This will turn the type of the test suite into test suite that needs a client environment. So you have to annotate this test suite with my server such that this entire test suite has access to this client environment and knows how to run a test that uses a client environment. And when you then run the test suite, exactly what you want to happen will happen. It will set up the web service once. It will then generate 100 arguments, run the test 100 times with that same web service without deleting any state in the meantime, and then at the end tear everything down. And it will test exactly what you wanted to test. That's everything for the real-world example of the web service. The last part is where I link to other projects that you may want to have a look at. The first link is to QuickCheck, which is the original implementation of the property testing. It's still on Hackage. We still use it to this day. The second is the HSpec testing framework that I use, or we use, to put the property tests in, and it allows you for this setup and teardown of the web service as I just showed you. Then the third one is called Validity, which is a library or a few libraries in which we've already prepared property combinators and property test suite combinators that you can just reuse, so you don't have to write associative or commutative or even an entire test suite for a monad that will be implemented for you if you just use type applications. The same thing for JSON instances, etc. Then there's also some research being done in this area, which is really exciting to me. The first one is QuickSpec, which allows you to discover properties of your code so that you don't even have to write the property tests anymore. You just run QuickSpec, it will spit out all the properties that you may want to test, and you can just copy paste them into your test suite. Now, there are some problems with QuickSpec. For example, it uses ridiculous amounts of time if you want to run it on a real real code base. So there's also another project that tries to solve this, which is called EasySpec, which does something special, which is called signature inference, to then run property discovery to make it fast enough and practical in real situations. But these two are research, and I wouldn't recommend using them on commercial projects yet. I just wanted to show you that there is more research being done here, and that the space will grow larger as we wait a bit longer. That's the entire talk I have prepared for you of practical property testing. If you have any more questions, now is the time to go ahead. Feel free to tell me to go to another slide and show it again so I can explain something.
You're getting some great jobs coming in. I'm not seeing any more questions coming in yet.
I'm getting jobs coming in.
Great job. Well done.
Oh, I thought you were suggesting that there were recruiters on the call.
Let's just give it another few seconds if people are still trying to type in at this point.
Yeah, take your time. I'll be here for a bit more time at least.
Okay, it looks like that's it.
All right. Super. Thank you very much for watching, everyone.
Hold on one sec. Actually, I think we do have one more coming in.
All right.
Just saw someone raising a hand. Oh, here we go. So in your example, you're basically testing if the call is idempotent. Are there other properties you find yourself looking for these sorts of projects?
Yes, there are, and that's actually why I linked to Validity as well. I can go into that for a bit more. Usually we have custom invariants on our data types. And when one of these values of this custom data type that has an invariant is produced by a certain function, I'd like to make sure that every time you run this function, you get a valid output, and not just an output of this type, but a valid one. So one of the tests I write a lot is that for any argument that you put into the function, your output will be valid. And this is not just important for pure functions, but also for web applications. Another example there is, oftentimes I want to check that a certain kind of flow of things you can do in a web application works, and it works independent of my username. And then instead of just writing a unit test with test username as the username, I can make that an argument that I use in the property tests. So essentially, even if you do nothing else, you can just replace the dummy values that you use in your unit tests and replace them by arguments to the property test, and you'll have a property test suite. Now, if you think, oh, that's fine, I don't want to run it 100 times, I just want to run it once, but it doesn't matter what the username is, then there are actually combinators that allow you to specify, I only want to run this part of the test suite, every property test only once, and that can work as well. You can actually put that as low as you want, or you can turn it up as well. And I like to, for example, generate a new random UUID for a user to make sure that it's not being used for any other property tests first before that. And then I make the combinator that says, with a valid new user, run this test. So this is something I find myself rewriting a lot. There are actually some libraries out there for a servant, for example, that allow you to assert certain properties for your entire API, so that you can say, for my entire API, whatever you do with it, it should never return a 500 error. And then QuickCheck will just go ahead and test that for you and see what happens. So that kind of reuse is also quite fun.
We have another question coming in. If there are any open source libraries that have good property tests that you'd recommend as a source of best practices? Oh, sorry, best practices, clever property testing techniques, inspiration, or anything else along those lines.
Oh, I guess I would suggest looking at my projects, but I guess that doesn't count. Let me think. The Cardano SL project uses property tests in a lot of its tests. So that's a cryptocurrency, and it uses a certain property testing combinator a lot, which involves serialization to binary data and back. And I actually think they do a lot of things very right when it comes to testing.
Cool. Okay. Oh, sorry, and one more. In big projects, how long do your property test suites usually take? Where do you draw the link with number of generated cases?
Yeah. So
draw the line. Yes, that makes more sense.
That makes sense. I've run into this problem a lot as well. Usually when your property test suites are too slow, it's not because you've run too many cases. It's usually because your generators are too slow. But even if you just use generators that always immediately generate the right value, that you run through such that, for example, even when you just generate the right values every time, and it still takes too long, you can turn down the number of tests you want to run per property. I guess my property tests should take no longer than the difference to be noticed between a unit test and a property test. And we get there usually. Sometimes it's a bit hard to generate data, but then those are cases where you wouldn't want to generate the data manually for examples anyway.
Okay. Thank you very much for the presentation. Everyone, thank you for attending. Great crowd, and looking forward to doing more of these in the future.
Me too. All right, let me try to stop this screen share.
Okay, thanks everyone. You'll see updates coming from us about the next time we're able to set up another webinar. And again, reach out to us on Twitter or anywhere else if you have any recommendations or requests for specific topics to be covered.